So, Prob Stat, section 8.3, continued, part 2. Environments, government officials, vehicle manufacturers interested in studying auto exhaust emissions produced by motor vehicles. Major pollutants include hydrocarbons, carbon monoxide, and nitrogen oxides, NOx. Random sample of 40 light-duty engines, same type, are looked at. The mean NOx reading, 1.2675 standard deviation, 0.3332. This is in grams per mile. And we want to construct and interpret a 95% confidence interval for the mean amount of NOx emitted by light-duty engines of this type. So, estimate the true mean, mu, emitted on light-duty trucks. So we're stating the problem, 95% confidence level. Our plan, if conditions are met, use the one sample t interval method to estimate mu. So our conditions met. Random, well, they said it was from a random sample of 40 engines. 10%, we're sampling without replacement. We're not putting the engine back, so we want to make sure that this 40 is not greater than 10%. So 10 times 40 is 400. Are there at least 400 light-duty engines of this type? I think there are. And then the large sample. We don't know about the population, if it's normal or not. But if n is 40, that's greater than or equal to 30. We should be safe using the t-distribution. So now we're going to do the calculations. X equals 1.2675 grams per mile. S of x is 0.3332 grams per mile. Degrees of freedom, 40 was n, so 40 minus 1 is 39. To get the t star, use the t-distribution. Look it up in the table. Uh-oh, no 39. So we use not the closest, like 40, we use the one that has, let's make it a little bit bigger. So instead of 2.02, we're going to use the 2.04 and make sure we include this 95% confidence interval. So 2.042 is our value. So it's x bar plus or minus t star times s of x over square root of n. So it's the statistic plus or minus the critical value times the standard deviation of the sample divided by the square root. All this stuff comes out to 1.2675 plus or minus this. Gives this interval. How do you state that? It's always the same. We are 95% confident that the interval from 1.1599 to 1.3751 grams per mile captures the true mean level of, go back to the problem, nitrogen oxides emitted by this type of light-duty engine. Suppose we wanted to do an experiment. We wanted to gather some data. How many things should we gather? How many people should we talk to? How do we figure out what n should be? Well, that's the sample size for a desired margin of error. And we're going to do it the same way we did the population proportion. We're going to, this ME is for the margin of error, and we want to leave n alone in our formula. So the ME is going to be the margin of error for this. We want that margin of error to be greater than or equal to this calculation. Now we use Z star because this will be a narrower, smaller value than the T star. And because that'll be part of the numerator, that'll make this a larger number. So we make sure we get enough of that. The sigma, we may not know that, so we might have to pull that from some other study that had happened or through experience. It's not like the proportion when we could take 0.5 as the worst case scenario. This one we need some sort of information to get that. Leave n alone, and then we have to have some margin of error that we can use. So let's try practice one of those. Estimate the mean cholesterol level mu of a particular variety of monkey, often used in lab experiments. Like to estimate within 1 milligram per deciliter. So that is our margin of error of the true value of mu at 95% confidence. Previous study involving this variety of monkey suggests the standard deviation is about 5 milligrams per deciliter. So this is our standard deviation we're going to use. Obtaining monkeys is time-consuming, expensive. Minimum number of monkeys will be better, but we need to make it satisfactory as far as the estimate. So 95, we're going to use the z-star, 1.96 instead of those 2.02s and 04s. A little smaller makes it a little, the numerator larger, which will make n large enough to be right. Sigma equals 5, our best guess for the standard deviation. So, and then solve for n. Remember, this margin of error we came up with was 1. So the 1.96 is the z-star, the 5 is the sigma over the square root of n, less than or equal to the margin of error, we came up with 1. Now you can just change these two because that's how you can work with a fraction. This is like the numerator with that denominator. And so we just switch those two, multiply this out, and 96.04. Well, don't choose 96, we better choose 97 to get the cholesterol levels. But not 100, that's too many. Or we don't have to pay for that. So we have estimated a population mean. We know how to state and check the random, 10%, normal large sample, 30, for constructing a confidence interval. Explain how these t-distributions are different, a little wider at the x-axis, they're spread. Determine the critical values using the t-star stuff. And construct and interpret a confidence interval for a population mean. Then determine the sample size. So we'll have some problems, practice problems for the review for the test over 7 and 8. But that's in a different set of slides. Thank you. Good night.